Hi, welcome to Chapter 2, Overview Part 2. We're going to cover sections 2.5 to 2.9. So the first thing we need to talk about is the periodic table, one of the most important things in chemistry. The periodic table is made up of periods and groups. Periods are your rows. And your columns are your groups. Elements in the same group, groups could also be called families, have similar properties. There's also this zigzag right here, and that separates your metals from your nonmetals. So all of the yellow elements here are your metals. So these are all your metals. So everything to the left. All of the green are your nonmetals. Notice hydrogen, even though it is on the left of the zigzag, is considered a nonmetal. And the elements touching your zigzag, but not all of them, are your metalloids. It's just the purple ones. So 1, 2, 3, 4, 5, 6 metalloids. When you look at the symbol on the periodic table, normally the number on top, it's a whole number, is your atomic number. If you remember from part 1, that is your number of protons. And on the bottom is your atomic weight, or remember, it's also known as your atomic mass. That is your weighted average that you got from your isotopes, which we talked about in part 1. Some groups on the periodic table have names. So your groups 1, 2, 6, and 7, and 8 have names. So if I go back to this picture for a minute, this is group 1A, 2A, and then it was 6A, 7A, and 8A have names. So this group right here is your alkali metal. This group right here is your alkaline earth. The last column here is your noble gases. And next to that is your halogens. And we've never really discussed the name of this column before, but that is called your, sure I'm spelling it right, chalcogens, okay? So using the periodic table, you could kind of determine what type of compound you're making and how to write the formulas. So what we see here are some molecules. And the subscript tells you how many of that atom there are. Now notice these two here are the same element. So remember what we learned in chapter 1. These are elements, even though they are molecules. They're molecules of an element because they are two of the same exact atoms bonded together. Okay? Most of your molecular compounds are covalent. So another name for covalent can be molecular. And they contain nonmetals. Also, it is important that you start memorizing these or remembering the 7 diatomics. And here they are: hydrogen, nitrogen, oxygen, fluorine, bromine, and iodine. In nature, they're never found alone. They are bonded to each other, so you will always find them as diatomics. Let's go back for a minute to your periodic table. So hydrogen's a diatomic, and then the rest of them make a 7 on the periodic table starting at number 7. And there are 7 diatomics. That's how I remember them. So there are 2 types of formulas. You have your empirical formula, which is your lowest whole number ratio. So you can't simplify it. Then you have something called a molecular formula, which is a multiple of your empirical formula. So an example I have here, your empirical formula would be HO, and then your molecular formula would be H2O2. So this is 2 times your empirical formula. Another example would be CH4 would be your empirical formula, and then C2H8 would be your molecular formula. So this is 2 times that. It doesn't have to be 2, it could also be 3. It is just some multiple. So if you know your molecular formula, you can determine its empirical formula. So if I told you, here's my molecular formula, what's the empirical? Well, you just simplify it so you can determine the empirical. But if I give you the empirical formula, you cannot find your molecular formula unless you know the molar mass of your molecular formula. Here are some ways to illustrate molecules. So you could just have the formula. So in this case, it would just be CH4. Or you could draw the Lewis structure, which they're calling here a structural formula. So that's your Lewis diagram. Or you could try to draw it in 3 dimensions where, like, see these little triangles here, this lined one and the solid one. That's to sort of draw it in 3D so that this H is behind the C and this one's coming out of the paper, kind of like your ball and stick. The nice thing about these two is you can get an idea about the bond angle. This is kind of what your molecule would look like if you could see it, but you can't really see the bond angles. And don't be deceived. In this diagram, it looks like the bond angles are 90 degrees, but they are not. You cannot get bond angles from those diagrams because they're just 2 dimensions. So now we're going to move on. So those last couple slides were talking about compounds that are mostly covalent, but now we're going to talk about ionic compounds. And ionic compounds are made of ions, and ions are charged atoms. So they could be either a positive or a negative charge. Your positive are your cations, and I always say the T in cations look like the positive side. They are positive because they lost electrons. If you lose a negative, you become positive. If you are a negative charge, then you're an anion because you gained electrons. What you need to remember is most metals form cations and nonmetals form anions. So if you look at your periodic table, if you're in the alkali family or group 1A, notice they all have a +1 charge. If you're in group 2, they all have a 2+ charge. And aluminum has a 3, and it's in group 3. Nitrogen is a 3- charge, so 3-, 2-, 1-, and the noble gases have no charge. Some of the transition metals have special charges, and on this slide I've listed some of the special charged ions, so keep this as a reference so you can refer to it when you have to write formulas. So your ionic compounds, and the most common one that we always talk about is sodium chloride, NaCl, table salt. All right, so what you are bonding when you make an ionic compound is a metal and non-metal. So remember, your metal likes to lose electrons, so it forms a cation, and your non-metal likes to gain. Once they do this, they form charges or ions, and these charges are attracted to each other, and that's what forms the bond. They don't form a molecule, they form a crystal lattice. So you have a repeatable NaCl, NaCl, NaCl going across the whole thing. So how do we write formulas for ionic compounds? Well, the first thing you want to do, and in our example here, is you write the symbol of your element with the charge that it would form when it loses or gains ions. Then you crisscross. You take the number that's on this and you put it down below, and then you take the number that is here and you move it over here. Sort of what they're showing you here. When you're done writing your formula, there should be no charge on your compound. So here it says the charge of your cation becomes the subscript of your anion. The charge of your cation becomes the subscript of your anion. And the charge of your anion becomes the subscript of your cation. What if these numbers are the same? Well, when you write your formula, you want to write it in the simplest whole number ratio, sort of like an empirical formula. So if I have calcium and oxygen, they both have the same charges. Instead of writing Ca2O2, it just simplifies down to CaO. Same thing here for magnesium sulfide. What if you have something called a polyatomic ion? A polyatomic ion is a group of elements that are bonded covalently together, but they act as an ion. So in this case, you have aluminum and your sulfate ion. Your sulfate ion has a -2 charge. You cannot do anything to the SO4. They're a group, they're a package deal. You can't separate them, you can't change the numbers on them. So what you do is you put parentheses around them to kind of protect them. So you have your aluminum, and you have your sulfate with your parentheses, and then you crisscross as if this was a single element. You don't touch what's inside the parentheses. Now, if you were placing a 1 here where the 3 is, because your element you were bonding with had a charge of 1, then you wouldn't need the parentheses. How do we name our ionic compounds? Well, you basically write the name of the metal, and then you write the name of the nonmetal, or your anion, with the ending of IDE. So if I had NaCl, Na is just sodium, and Cl is normally chlorine, but we change that to chloride. You change the ending to IDE for the anions. If you have a polyatomic ion, you just write the name of the polyatomic ion. So here I have aluminum, NO3 is nitrate, so it's aluminum nitrate. Now, it gets a little bit tricky with ionic compounds when you have a metal that has more than one charge. Iron can be a 2+ or a 3+. So you have to use Roman numerals to tell me which charge you're using. Okay, so if you have a metal with more than one charge, you have to use Roman numerals. If I could only spell. So remember, that's 1, that's 2, so on and so forth. I found this interesting in your book. Sometimes it's hard for you to remember polyatomics. So if you kind of memorize the polyatomics that end in ATE, so like nitrate and sulfate, if you remove an oxygen from them, the 8 becomes an ite. So if this is nitrate, you remove one oxygen, it's nitrite. You remove one oxygen, it's sulfite. So if I had CO3, 2-, that's carbonate. What do you think carbonite would be? I remove one oxygen, it becomes an ite. Then your book kind of had this little pattern to help you remember polyatomics. It says the center atom on the second row of the periodic table have a bond to at most 3 oxygens. So this would be your second row of the periodic table. So your carbon bonds to 3 oxygens. And then your nitrogen bonds to 3 oxygens. And that is your polyatomic that ends in ATE. Then it says your charge increases as you go from right to left. So notice this charge is 1, and then it increases to a -2. Now on the third row, your oxygen can have up to 4. So your phosphate, sulfate, and perchlorate have 4 on them. And then your charges, this is -1, -2, -3. So if that helps you remember your polyatomics, it's a nice little pattern. Sometimes it's easier to remember patterns than to just memorize. So here are some patterns with naming the polyatomics, okay? So, and it's similar if you remember when we did naming acids. The polyatomic with the fewest oxygens would have a hypo and an ite on it. So you take your common polyatomic, which is the one with ATE, okay? If you have one more oxygen than the common, so we're going to call this common, you put a prefix per. This means one more oxygen. If you have one less, your ate becomes an ite. If you have 2 less, you keep the ite, but now you put a hypo there. Remember, this is for polyatomic ions. So let's kind of incorporate this into acids. Your acids are when you take hydrogen and you bond it to a polyatomic ion. And there are 2 types of acids. There's your binary and your oxyacids. Binary have 2 elements, and you use hydro when you're naming them. So like HF would be hydrofluoric. Your oxyacids have polyatomics that have oxygen. So they follow the same rules that your polyatomics follow. So you have your common acid, and instead of 8, you change your 8 to an ic. 8 to an ic. So here's your common acid, and you make it chloric acid. If you have one more oxygen, it becomes perchloric. One more. If you have one less oxygen than the common, your ic becomes an us. If you have 2 less oxygens, you have hypo us. And remember, if you're a binary acid, it's hydrochloric. That's how you name your acids. How do we name our covalent compounds? Your covalent compounds, you're going to use prefixes. And prefixes are going to tell you how many of that element you have. So remember, covalent is when you have 2 nonmetals bonded together. And the first nonmetal that you're going to write in your compound is always the element that is furthest to the left in the periodic table or lower in the same group. Okay. And once you are naming it, if your first element does not have a subscript on it, you just write the name of it. So C is carbon. The second one, you use a prefix to tell me how many you have. So this is dioxide because there's 2 oxygens. If your first element has a subscript, you must use a prefix. So this is dinitrogen because there's 2 nitrogens. There's only 1 oxygen here. You have to tell me there's only 1 by saying mono. Now, if your prefix ends in an A or an O and your element starts in an A and an O, you don't want to have too many vowels next to each other. So notice here you don't have 2 O's for monoxide, okay? Organic compounds. So if you have a compound where you have carbon and hydrogens bonding and they're all single bonds, they end in ane. And your prefix that goes with that ane depends on how many carbons you have. So if you have 1 carbon, it's meth. 2 carbons, it's eth. And 3 carbons, it's prop. The easiest way to remember your prefixes is this mnemonic down here. Monkeys eat peeled bananas. So meth, F, prop, and then the next one would be bute. So if I had 4 carbons, it would be butane. So monkeys eat peeled bananas. So instead of having all your carbons bonded to hydrogens, if you have one of them bonded to an OH group, a functional group, OH, then they become alcohols. So instead of ending, you have to add this OL for an alcohol. Alcohols end in OL. The prefixes are still the same. So this would be methanol, ethanol, and propanol. Okay. And that is the end of part 2. If you have any questions,